Let's take a look at a couple of graphs here today that we have. One that we're going to work on that has to do with relative age. Goes along with what we were talking about the other day when we were taking a look at all of our rock layers and what comes first, and our 9 rules that we had up on the board. Then after we look at that, we're going to look at a chart that looks like this that goes through radiometric dating. And we'll talk about that in a few minutes, and where it talks about the parent life and daughter life as things radioactive decay. So we're going to go over both of those. So let's do this one first because it's a little bit more of a review. We have rock layers X, T, Y, W, A, and B. And in these rock layers, we have different types of rocks. This is our limestone, sandstone, shale, igneous intrusion, and a fault. We know from our rules that intrusions and faults are younger than the rocks they go through. All right, so that means that the fault here is younger than B, A, Y, T. That this intrusion W here is younger and came after B and A were laid down. What that means is that if I had to ask a question, if I have these rock layers and then I have a fault line that goes through them, and a question that might be asked about that might be, the layers had to be that if the horizontal layers of rock have a vertical fault in them, that would be this, running through them, how might a geologist use relative dating to determine when the fault would occur? Well, what you would say is that layers B, A, W, Y, and T had to have been laid down before the fault. So, B, A, Y, and T laid down before the fault. With that said, that then tells us that the relative age of the rocks is older than the relative age of the fault. So the relative age of the rocks is older than the relative age of the fault. That's how you would say that. Now, the next thing that we want to look at is we need to be able to put our rock layers in order. And always be careful when we're doing this on what are they asking you for? What order are they asking you for? So in this scenario, we want to put these in order from youngest to oldest. I always find that's easier to do because you can kind of start where there's not a lot of messiness going on. So our youngest layer is our very top layer here, which is X. Notice we have a little bit of erosion going on here in T, but that's not written there. So we have that. Now we'll notice we have this fault line, and we said before that the fault line is younger than everything it goes through. So it's younger than B, A, Y, and T. So that fault line is going to have to be next. It's not labeled, but we'll put it there. Next, our next line is going to be T. And then after that, it will be Y. And then please look again, we have an intrusion here. And what did we say about intrusions? They are younger than the rocks they go through. This intrusion goes through B and W, so that means it must be younger. So our next one is A, and then W, B. That's youngest to oldest. And this way would be oldest to youngest. Please always be sure you know what they are asking you for. Take the time to read that. Okay? The next thing that graph I want to have you take a look at that goes along with this relative absolute age is this graph that has to do with radiometric dating. Okay? And radiometric dating is how we find the absolute age of our rocks or another object. And the absolute age is the actual age. Not comparing it to something else, but the actual age. Here, when I use this example, please note that I'm going to be using 100 grams here, not the 80 that's on your sheet. So please make sure that you change that a little bit. So change that so that you can see that, okay? Now, radiometric dating is calculating the absolute age of a rock, measuring the parent and daughter material. Now, we know that when materials radioactive decay, they go from a parent isotope and decay into a daughter isotope. This takes a certain amount of time, and we call that time half-lives. So, for example, when we're looking at this material right here, at one half-life, I'm going to lose 50% of my parent material is going to become a daughter material. It becomes a new isotope. So your daughter material is a new isotope. Okay? And after the next half-life, the second half-life, I'm going to lose 50% of what I had before. So I had 50% here of my parent life. So now I will have 25% parent life and 75% daughter life. In my third half-life, I will then lose half of my 25%, which is 12.5%, making my daughter 87.5%. My next half-life, my fourth half-life, I will lose half of my third half-life, so it will be 6.25, and my daughter will be 93.75. Please notice on this graph, it really stops at fourth life, and this is only 100% after many lives. This is not after the 5 half-lives. Because at 5 half-lives, I would have half of my 4, which would be 3 what would that be? And half of my half-lives, it would be half of 6.25. So it would be 3.125. Okay? It would be half of that. And then that means that this one would be 96.875. Okay? So this is my parent. This is my daughter. After 6 half-lives, I would have half of 3.125 parent left. It keeps going down as we go along. All right? For every half-life. So let's take a look at our graph here. Now, if I have a sample of radioactive element and it has a mass of 100 degrees, I know this 100 grams, and I know this is kind of hard to see, but you have the sheet in front of you. How much parent and daughter material are the sample after 2 half-lives? So this, I have 100 grams that I start off with. And after 2 half-lives, I have 25% parent and 75% daughter. That means I'm going to have 100 grams times 0.25, and that's going to give me 25 grams. Here, I will have 100 grams times 0.725, which is 75 grams. So that's how I would figure out a problem like that. Now, what if they asked you a question like, say for example, looking at my chart here, if 12.5% of the parent remains in the rock, what half-life, how many half-lives has gone by? Well, let's take a look at our chart. Where do we find 12.75 in my parent? So we know the parent is the dark colors. This is 50%, this is 25%, and this is 12.5%. So that would be after 3 half-lives would be the answer there. Okay? So that kind of breaks it down on how we can find absolute age by using radiometric dating and using a graph like this. Remember to take time to look at your graph and to realize that the dark color is your parent, that you use half of it each time. Different isotopes break down over different periods of time. So for example, carbon-14 will break down 5,230 years for one half-life. So this is going to take a great deal of time for this to happen. Some of them do it in millions of years, some of them do in seconds. So whatever you're going to use to date needs to have broken down in that time period. So for example, carbon-14 dating is really used well for items less than 75,000 years old, because when we start to run out of material by then. So for example, if I wanted to date the age of the Earth, I would not use carbon-14 because we know that it's much older than 75,000 years old. Okay, I hope that helps you get started.